Hello, everybody. I think we are ready to slowly start this session. First, we start with the sponsor slide. Thanks to our sponsors that enable this event. And now, welcome to my session, Data Overview and Manipulation with demos in Transact Sql, R, and Python. I am Dejan Sarka. I am quite long in this field, have around 35 years of experience, been a data platform MVP and MCT for more than 20 years, authored, co-authored 18 books so far, more than 20 courses, and I'm focusing on this area, data science, data quality, of course, also data modeling. In this presentation, I will talk about this huge topic, a topic or a task where you spend 70, maybe even 80% of time in your data science project with data overview and data manipulation. Of course, I will just scratch the surface of all of the possible problems, but I will quickly describe and explain what are data sets, cases, and variables, and then how do we check the distribution of these variables using population moments and graphs, introductory statistics for discrete variables, centers, and spreads for continuous variables. And then I will talk about handling missing values and outliers, and classical tasks when you have to create numerics from strings, or add derived variables, or create discrete variables from continuous ones, maybe even strings. And when talking about discretization, I will also talk about something that is not so frequently used, equal height discretization. And in this moment, I will also briefly introduce entropy, and with entropy, with help of entropy, show why equal height discretization is useful. So first, few definitions. These expressions come mostly from statistics. With data science algorithms, we analyze cases, and this is the entity we want to categorize, classify, or whatever. So it's a customer, it's a product, it's a loan, or things like this. And each case encapsulates all of the information we have about an entity in variables, also called features. All cases together form a data set. In R or in Python, we usually work with a data frame, which is a matrix. So we still have positional access and the order is preserved. Of course, in SQL Server or in any relational database management system, we are representing matrices with tables where we have only one way of accessing the data. We get a value with table name, key value, and column name. Now, first, before we even start analyzing, we have to realize how our variables or our columns in our table measure data values. We have two broad groups, discrete values and continuous values. So discrete are variables where a variable can take a value only from a very limited pool of values, like 5, 7, plus minus couple of values. And these values could be only categories or names for the category with no natural order. Then we have nominals or categorical variables. But we have also variables where these values have some internal order, even if they are strings. And this order might not be alphabetical order for strings. For example, if we represent education as string, we know that values have some intrinsic order, and these are called ordinal variables. If they are numerics, also called ranks. They have order, but they do not permit arithmetic. And continuous values are numerical values. True numerics support all arithmetics, but we can also have intervals where and this is very typical in business, where these values are limited at least on one side, if not on both sides. With intervals, not all arithmetics make sense. For example, summarizations many times make no sense, but subtractions make. If you look at the temperature, it's an interval with absolute zero on the left side, and summarizing two temperatures usually makes no sense. Now, for continuous variables, we want to know how the distribution function looks like. Of course, we can always draw a graph. We have strong graphic support in Python and in R. Also, we could use other tools like Power BI. However, sometimes we have to deal with many variables, and also we have to compare multiple variables, and for comparisons and dealing with many variables, numbers are much better than graphs. And then we describe the distribution with descriptive statistics. We calculate centers of a distribution, spread, and higher population moments like skewness and kurtosis. Definitely, we do not want to deal with mean only. Mean is probably the mostly abused measure in statistics. Mean by itself really doesn't mean a lot. At least we want to have also median, which is the value at the half of the cases. And then if median is much lower than mean, then we know that we have some long tail on the right side. For example, let's say that we are measuring wealth, and for some reason, some of these wealthiest people, like Jeff Bezos or Bill Gates, join this session. Suddenly, in the average, we are all billionaires. However, median would be much lower, so we know we have some tail on the right. If median is greater than mean, then we have some tail on the left. And with higher population moments, skewness, we are measuring whether the tail is on the right or on the left, and kurtosis, how important the tails are. Of course, in case of having a lot of variables way, or a lot of cases way out of the mean, then we have high spread in the distribution, and the standard measure is standard deviation, but we can also use interquartile range, read the value on the third quartile, subtract the value on the first quartile, and compare it to standard deviation. If it's greater than standard deviation, then tails are not important. If it's lower, then tails are important. And how important the actual measure is kurtosis. So we have these options. We have normal distribution, we have positively skewed distribution, long tail on the right, or important tails, or both sides, we have tailed distribution. However, you should always check the graphs as well. Just a brief overview. I know it's kind of hard to check 500 graphs if you have to deal with 500 input variables. You use numbers to quickly get understanding of the distribution, but a quick blink or a quick overview of graphs can get you the idea if you have some extraordinary cases, some weird distributions where numbers could mislead you. So you can use histograms, bar charts, scatter plots, and more. I will show you the famous Anscombe dataset. This Anscombe was a statistician, found this dataset already in the 70s. And let me go immediately to my first demo. I will start with R in RStudio, load the Anscombe data, and show you what is the problem with this data. So in this data, I have only 11 cases with 4 pairs of variables, x1, y1, x2, y2, x3, y3, and x4, y4. And let me calculate the correlation coefficient for these 4 pairs. And what you can see is that it's always practically the same, 0.816. These first 3 leading numbers are always the same for all 4 pairs of variables. Now, let me show you these variables on a graph. I will create a trellis chart with small multiples and create a graph of these 4 pairs of variables, and what you can see is that distributions differ completely. In the top left graph, I have quite normally distributed values, so I can trust the correlation coefficient, and it looks like the correlation or the association is linear. In the second graph on the top right, I see that there is some association, but probably not linear, although the correlation coefficient is the same as for the pair on the left. At the bottom, I see practically perfect linear, bottom left, perfect linear association. However, probably the slope is too high because I have one outlier. And bottom right, I see that there is practically no correlation, that the x is constant, but I have one very, very far away from one case, very far away from others, one outlier that changes the picture completely. So combining graphs with numbers is always recommended, although, as I said, if you need to deal with hundreds of input variables, you probably don't want to spend too much time on graphs. So for discrete variables, we use frequency tables and graphs for the basic representation. We want to show value, absolute frequency, absolute percentage, cumulative frequency, cumulative percentage, and histogram. Please note that cumulative frequency and cumulative percentage make sense if this variable has some intrinsic order, if we are talking about ordinals. And you should make sure that you properly order the ordinals. So let me show you some examples. Now in R, I will read data from AdventureWorks DW database from target vtarget mail view. And let's start with plot of education. And I will start in a naive way without ordering. So what I can see here is that it looks slightly weird, this distribution. For education, you should expect a distribution that would somehow resemble Gaussian. We have some people really highly educated, some people with low education, and most of the people in the middle. This doesn't look much Gaussian. Of course, the education is sorted alphabetically. So let's inform R about appropriate order. So I will create a factor, categorical or and ordinal variables in R. Discrete variables are called factors, and I will explicitly list levels in the correct order. So let's do this, and let's make the plot again. And of course, suddenly this plot looks much better. Now let me jump to Python, and I already preloaded all of the libraries I will use. And let's connect to my SQL Server, read the data, the same data as in R, check some information about this data set. I have 18,484 cases with 13 variables. These are first 10 rows with couple of columns, and 3 dots mean that there is not enough room to show all of the values. And let's check the basic distribution value counts of education. Again, you can see that we have this education sorted alphabetically. Of course, our education is just an object, general object. Python is also not informed that this is a discrete or categorical variable. So let's define it in Python, and let's check. And now Python is informed that this is a categorical variable. However, the order is still alphabetical. So let me reorder it and define properly categories. And check now And now I see that education is categorical with proper orders of levels. So let me do value counts with using this index. So I get somehow Gaussian distribution. And let me check also this on the bar chart and show the bar chart in Python, and I see very similar picture like I saw in R. Now we have many other options. For example, we can use Seaborn library in Python and show multiple variables in a bar chart. So this is education and bike buyer, and we can see that we have more bike buyers with people with higher education. Please note that you wouldn't be able to notice this association if you wouldn't properly order education. Now, can we do the same thing in Transact Sql? Of course, Transact Sql is not really prepared for a lot of statistical analysis. Let me use some other variable, in this case, commute distance. And here is my here are my distinct values, and you see that they are not sorted properly. Alphabetical order is not correct. So I have to reorder them, and I will simply use case expression to reorder them, and then calculate the absolute frequency, and then calculate the absolute percentage, like absolute frequency divided by the number of cases. And then this makes already some sense, right? This is already something useful, but I would also like to have cumulative values. Cumulative values make no sense if you are dealing with categorical variables, but since this is an ordinal variable, I will use window aggregate functions to get the cumulative values as well, and then also use the replicate function to create a small histogram in the same result set. Let me execute this whole query, and this is all of the information I need for my commute distance. And since I used case expression, also I can see that the values are ordered correctly. There are many ways how you can do the same thing in R. For example, very popular is package DSCR, and here is function freq that is actually calculating frequency, percentage, cumulative percentage, and also generating a quick histogram. So in general, you see that we have many ways how to calculate this. And this is the result we wanted to get. Now for continuous variables, we use descriptive statistics. We use population moments. We start with centers, and we already know that mean by itself makes no sense with any other measure. At least we should list also standard deviation and median. Mode could be also useful. This is the most common value in the distribution. Useful is to know if you have more than one peak, if you have 2 or 3 values that are the most frequent, so you don't have really a distribution that would completely follow the Gaussian curve. And especially comparing median and mean gives you information about skewness. Of course, spread is extremely important. We can calculate spread naively, like range, maximal minus minimal value. Of course, one outlier would make a lot of difference. Therefore, similarly, like we calculate median for the center, not just the mean, we can calculate interquartile range. As I mentioned, this is the value in the 3rd quartile minus the value in the 1st quartile. So before I continue with demos, let me also introduce another expression, another statistical term, degrees of freedom. This is important when you work with samples, not with full population, when you work with small samples. When you deal with SQL Server data, nowadays, this is not really a big deal anymore because you have enough rows, enough samples, but traditionally in statistics, degrees of freedom are much more important. So this tells you how many pieces of information can help you with the calculation. How many pieces of information are free? Imagine that you have a variable with two possible states, yes, no. And if you know the probability for state 1, let's say 0.6, of course, the second state is not free. You can calculate the probability, you know the total probability is 1. Or if you work with percentages, you can calculate the percentages left. If you have 3 distinct values, if you know 2 of them, the third one is determined. So in general, when we have n distinct values, we have n minus 1 degrees of freedom. And then we calculate the variance. So we square the deviation or the distance of every single value from the mean, square that we get positive numbers also for negative distances. Otherwise, the total sum of these deviations would be always 0. And then we divide this by the number of degrees of freedom. And this is the variance. For the population would be difference only in the first element. Instead of 1 divided by n minus 1 would be 1 divided by n. And you can imagine that when you have a large sample, then this quotient, it really doesn't matter whether you use variance or variance for the population. Standard deviation is then square root of variance. And this is the most general information about how spread in your variable. However, standard deviation is an absolute measure. Variable that has bigger scale than another variable would probably also have bigger standard deviation. So we need, in order to compare multiple variables, we need relative standard deviation, which is also called coefficient of the variation, simply standard deviation divided by mean. And this is an important piece of information. We call variables variables because we want to have variability in them. If the coefficient of determination is very low, there is no variability. So these variables are not useful in further analysis. So let me do some calculations. Let me this time start with Transact Sql. Doesn't really matter which tool you want to use first. So mode is simply achievable with Transact Sql by the top operator and with ties if the distribution is multimodal, has more than a single peak. With so many cases, it would make sense to maybe check groups as well, to maybe group ages. However, if we are working with single years, then we have one mode. Median, I will just use percentile count function. There are many different solutions how to calculate median in Transact Sql. However, since we have this window analytic functions like percentile count, it is easy to calculate median and also interquartile range. So let's check the median of age, and I see it is 32. Let's check also arithmetic mean, and it is 34. So we have median that is lower than mean, slightly, not much. This means we have some, but not really, probably not really important tail on the right side. Let's calculate also the spread. We can calculate, use min max functions to calculate the range. And of course, percentile function again to calculate the interquartile range. And we see that interquartile range is 17. So let me calculate also standard deviation for age. And then I will also calculate standard deviation for income and coefficient of variability for age and coefficient of variability for income. And let's see the results. So let me comment these results. First, standard deviation for age is less than 12, while interquartile range was 17. Because IQR is bigger than standard deviation, apparently tails are not over important. Now let's compare standard deviation of age to standard deviation of income. And of course, you can see that age is less than 12, while income standard deviation is more than 32,000. Yes, these are absolute measures, so you cannot really compare these two variables. However, when we compare coefficient of variation, then we see that coefficient of variability or coefficient of variation is much higher for income than for age. Relative measures are, of course, extremely important. Let me switch to Python. I didn't really check what I have switched to until I saw this screen. So we have in pandas, we have describe function, which very quickly gives you information about a variable. So we get count for age, we have mean, standard deviation, minimum, maximum values in the first quartile, second, which is median, and third quartile. Of course, I can use separate functions like mean, median, and again, I see that median is slightly lower than mean. I can use minimum, maximum functions and get the range. I can check values on different quantiles and calculate the interquartile range. And then I can calculate variance, standard deviation, and coefficient of variability. Let's also check. Let me go to R before I come back to Python. Similarly, like describe pandas function in Python, we have summary function in core R. It gives me minimal, maximal value, first quartile, third quartile, median, and mean. And then I can calculate centers with separate functions and spread with range and interquartile range and variance and standard deviation and coefficient of variability. Now, of course, with Transact Sql, I cannot do much more. I don't have tools for graphs, but graphing is extremely powerful in both R and Python. So I will create multiple graphs for a very condensed overview of my data. So I will also create a small subset data frame, TM1, small subset of data from target mail, and create a cross tabulation of number of cars owned and bike buyer, split the screen to grid 2 by 2, so I will have 4 graphs in a single screen. And then I will use the plot function to plot education and marital status together to plot the distribution in this kind of combined bar chart. And I will create a simple histogram of number of cars owned and line chart for total children and number of cars owned. In this case, I am using the smaller subset because otherwise line chart would be very hard to read. And let's also check grouped bars for number of cars owned and bike buyer. And let me show you this result. So what I see is that besides getting the distribution of a single variable, like for number of cars owned, I also can see that there are some associations between variables. Definitely, again, I see association between education and marital status. You see that the higher education, the more married people. Also, it makes sense that we can also notice that there is some association between number of cars owned and bike buyer, so more buyers with less cars. And there is okay, this is very, very small subset of data, only 10 data points, but still it is an association between the total children and number of cars owned. And let me do some overview of data also. With Python, again, I will just select first 200 cases for scatter plot and do the scatter plot of yearly income and age. And I see, again, might notice that there might be some association between these two variables. However, it doesn't look really linear. If you look how, if I would try to draw a line here, it would go up with the age until some point when it goes down, which is very close to real data. When you start your working, you don't earn so much as later in your career, but at some point, of course, you start earning less. I can also use very nice join plot to show the associations of these two variables and also marginal distribution. And okay, this scatter plot is not clear enough, but I have better hit plot. Let's show this one. And in this case, I'm using all or kernel density estimation plot. I'm using all of the data, so it will take a couple of seconds more to create this plot. Now it's completely clear that age and incomes are associated, but we have two different ways of association, and we also see marginal distribution of age and marginal distribution of income. So together with graphs, we can really get good overview of data, descriptive statistics plus graphs. Let me also show you the trellis chart or chart with multiples in Python. So I'm showing, let me show the complete graph, yearly income in groups of bike buyer and house owner flag, and yearly income histogram with five bars. And again, I can see that buyer equals 1, house owner flag equals 1, income is higher than, for example, house owner flag equals 0 and buyer equals 0. Okay, of course, we could talk forever just about data overview, but let's spend the second part of this presentation with some really most common tasks with data preparation. So first thing that you have to deal with are missing values. And if you don't have enough data, you cannot really expect good analysis. So what do you do with missing values? Well, it depends how many of them there are. There are many ways how you deal with them. And the way that I prefer is the second way, filter the rows containing the missing data. However, before you do this, you must have a couple of prerequisites. So rows containing the missing data in any column. If there is too much missing values, too many missing values, you might filter the majority of the rows. So first condition is not too many missing values. And second condition is that there is no pattern in missing values. Otherwise, by filtering those rows, you are building the pattern in your analysis. So your analysis will be meaningless. How do you check if there is a pattern? Maybe you can just create a small indicator whether a variable with two values, 0, 1, 1 could mean there is a missing value in the row. Add this and then try to explain this variable, check the graphs with other variables to see if this variable is somehow associated with other variables. What else? Anything else is worse. Do nothing. Okay, if the missing values are not important, or maybe some algorithms do not care about missing values, you can just ignore them. Filter the columns means you are lowering the number of variables you are using, again, you could have then a very, very inaccurate model. There you can separate models with, without missing values. You try to predict or assign missing values, define how to assign them. Many times people want to substitute missing values with mean or with median. Please note that although it might be useful, you are lowering the variability this way. Modify the operational system so that you can collect the missing values. Yes, this is this ideal option, and any ideal option in real life, many times it's not achievable. It might mean years before you can get there. So probably a nice wish, but you are in the middle of the project, so you cannot wait 2 or 3 years before the customer manages to modify the operating system. Similar problems are with outliers. You saw the ANSCOMP data set. A single outlier has changed the picture completely. These are rare and far out of bound values. And before handling them, determine if there is any pattern, or even before that, before determining pattern, first determine if this is an error. You check, find these outliers, maybe it's a simple error. But we already know that in real life, there might really be some outliers. So again, if there is a pattern, then you should be more careful and check what kind of pattern is it. And maybe if there are not important outliers, you can do nothing. Maybe again, filter rows, ignore columns, replace outliers with means, or this could be useful, discretize continuous variable into a new variable, and these outliers, for example, people with very high income are hidden in the last class of the new discrete income variable. Or you can use some technique for data normalization. Instead of using the continuous data, the full range of continuous data, you normalize this data in some interval. You can use some normalization functions like range normalization to get all data in interval between 0 and 1 or between -1 and +1. Now, sometimes you need to create numerical variables from strings because some algorithms accept numeric variables only. For example, regression algorithms expect numerical variables. For ordinals, you just use this order or index. For nominals, remember, for nominals, each categories have no intrinsic order. A category is just the name for the class. So in this case, you create what are called dummies, dummy variables or indicators with values 0, 1. For every distinct original value, you create a new variable. For example, if we have marital status merit single, then we have 2 new variables, merit single, and the first one, merit, will take value 1 when the original variable had value merit, and so on. And then you can use those in numerical analysis. However, please note that these variables, if you have, let's say, 3 distinct or 4 distinct values of the original variable, you have 4 new variables. In further analysis, you shouldn't use all 4 of them. This is an important information. Very simple, but people many times make this small mistake. Why? Because all 4 of them are perfectly associated. Remember, this is connected with degrees of freedom. If you will know the values for 3 of them, we will know the value of the 4th one. So simply in further analysis, use only 3 out of 4, and whichever you choose. But otherwise, you will have in input variables perfect association, and this will have influence on further analysis. This is a very, very important task. Derived variables, very important, also could be very, very long. I will not spend too much time on it because it's mostly depend on the business knowledge, on the knowledge of the problem you are solving, how to define these derived variables properly. Many times in your source data, basic variables are not very useful. For example, you already know from medicine that obesity index is much more important than basic variables height and weight. And of course, this kind of variables can be found really if you are the subject area expert or if you have a contact with the subject area expert. And these variables are then much more important than basic variables. Sometimes you can even solve a problem with missing information by extracting features. Sometimes you can find some information from variables that look like they don't have any information. Of course, product zip code have a lot of zip codes, post-it codes have a lot of information, universal product codes have a lot of information. But again, you must know the subject. You know that zip codes, for example, in Canada are random, don't tell you the geographical location. You must know these things. Even columns that are auto-numbering, like identity property in SQL Server, could be useful. Usually it means that higher number means that that case came into the data set later than case with lower number. Okay, let me show you a couple of examples. So I will just show you examples first for handling nulls. I am filling a very small table, null test, DB on null test with a couple of rows. Let me show. Let me show this without the next comment. So I have just a couple of rows with, oh, now I inserted data twice because of that syntax error. Let's go again without the last comment. So I have 5 rows, and row 4 is the only row where none of the columns has null. So in Transact Sql, we can use isNull or coalesced functions. We should know how aggregate functions work. Remember that in Transact Sql, aggregate functions are just skipping nulls. So for example, average of column 2 is 8, sum is 24, count is 5 rows. If you divide sum by count of the rows, we have 4.8. So remember, in column 2, I have 2 nulls, and these 2 nulls, of course, were simply skipped by the average, which was simply 8. Now let me switch to R, read this data, connect to my SQL Server, check this table, and what can I do? I can just omit. This is the simplest way. So the simplest way is simply delete all of the rows that have any not applicable NA value in any of the column. But I'm left with rows only. So in this case, this could be problematic. With isNA, I can check which values are null or missing, which not. Let's check the aggregate functions in R. And what happens, because I have nulls or missing values in this column too, also the mean is not applicable or missing. This is completely different than it was in Transact Sql. These are small things that you have to know. You have parameters for aggregate functions, na.rm equals true. Please note that dot in R is just a part of name. It's not a namespace. It's not like table.column or something like this. It's just part of the name. So the name of this parameter is na.rm. And then we have the similar result like we have with average function in Transact Sql. Let's switch to Python, connect to my SQL Server, read this null, and this is this null is here marked with none, not a number. Let's check. We have pandas isNull function that works very, very similar like the function we had in R. And then we have drop NA function, and we can use axis, and we clear all rows that have null in any of the column, or we can also remove columns. I have only 3 columns, and all 3 have some nulls. So in this case, my final data frame is empty. Let's check the aggregate functions, and I see that in Python, the mean aggregate function is working like it works the average function in Transact Sql. We have parameter skip NA equal false, and then I get the same result as I got in R, not a number. So it simply means it was missing. Okay. Now, when we talk about discretization, then of course we have to deal with, I have also to show the demos for derived variables and for getting numerics from strings. Now, before that, let me explain the discretization. This is the opposite process, getting categorical variables from continuous one. And there are many discretization methods. The most important 3 are equal with, equal height, and custom. So why would you discretize? One thing is that you can get rid of outliers. Next thing, some algorithms like Bayesian inference accept discrete variables only. And another thing is with discrete variables, maybe you can compare values that otherwise would be harder to compare. I have this first example, call length. This was a research that I was involved, a European research about calling habits. Call length is a very important piece of data, very important variable for this analysis. And the problem is that average call length varies a lot in different countries. Of course, you can imagine that the longest is in Italy. It was like twice longer than the second longest. And this way, Italian data was harder to compare to other countries. But by discretizing call length, we got comparable values. Now, equal with means classical discretization. This is how you would start with. Equal with means you create new data with equal ranges, equal width of each new class. Let's say from 1 to 10, then from 11 to 20, 21 to 30, and so on. Equal height means you have approximately the same number of cases in every subclass. And this is, for example, how SQL Server is creating its own statistical pages for key values of an index. And the question is, why would you do equal height discretization? And finally, you can do custom discretization, where you can, again, use your knowledge of the problem and knowledge how data is stored in your variable, and you know what you are analyzing. So let's say, for example, age. Many times you want to have narrower classes with younger people and broader with older people, but it can also depend on the problem you are trying to solve. So, for example, remember when you were young, like difference between 15 and 16 years old might be very, very huge, while difference between 65 and 66 might not be that important. On the other hand, if you are analyzing older people, then you might even go to the opposite direction and create narrower classes at the end. Now, the question is, why would you use equal height distribution, discretization, and why does it do SQL Server, for example? What is the point here? And the point here is that you minimize the loss of entropy. Entropy doesn't come from statistics. It's a measure of for the amount of information in a variable that comes from information theory. And more states means higher theoretical maximum for an entropy, more distinct states. So when you are discretizing, you are lowering the number of distinct states, so you are losing entropy. By discretizing to classes with equal number of cases, the loss is minimal. Let me give you a brief example. Now, before you start complaining about political correctness, I will start with 2 genders, but we'll add third in a minute, so don't start complaining yet. So we have 2 genders. Now, information is the same thing as surprise. Let's say that you want to know what will be the gender of the, you want to bet on the gender of the person that you draw randomly. So with 50-50 distribution, you will have 50% for surprise. Let's say that you have one gender 90% and second 10, you would bet on that gender and you would be surprised only in 10% of cases. Of course, maximal surprise is with 50-50 distribution. Now let's add the third gender. Now the maximal surprise is with 33-33-33. You are surprised in 2/3 of cases. And with 4 genders, you could be maximally surprised in 75% of cases. So more distinct states means more maximal entropy. And when you discretize, you lose some entropy. So with discretizing to equal height, the loss is minimal. Why would you do it? Well, let's say that you don't have a clue how you would do the custom discretization, then probably you would go for equal height for further analysis in order to minimize the loss of information. And the information is like variability, similar measure. Now, what about equal width or equal range discretization? Is it also useful? Yes, this could be useful because it's kind of preserving the shape of the distribution. So you might want to represent a continuous variable with a histogram, then you do equal width discretization, otherwise you lose the shape of distribution, and this is what we have already done. So let me go to demos, and of course for getting numerics from commute distance, I will use case expression again, and I will just, instead of assigning strings, I will just assign numerics 1, 2, 3, 4, 5 to different categories. And I have commute distance integer. For dummies, I will use the IIF function, and for marital status, I will generate 2 new variables. Let's create a derived variable, an example. So we have variables marital status and number of children at home, and I will create a new variable number of people in the household, and I will say 1. This is the customer, her or himself, and if marital status is married, I will add on 1, and then I will add number of children at home, and I get my derived variable number of people in the household. Now let's bin or discretize age. First, for equal width, I need to calculate the range, minimum, maximum, and then get the bin width. I want to create 5 bins, and then I can do the equal width binning. Not very nice, a lot of code, a lot of possibilities for case, but I get equal width binning. Equal, I'm ordering by new ID just to get kind of random order. Equal height binning is much simpler in Transact Sql. I just use entile function, entile 5, and then some variables are, or some cases are in the first bin, and then some in the second, and so on. And the number of cases in each bin is practically equal. 4 additional cases go to first 4 bins. Custom binning is again with case, and then you get custom bins. How do you do this with other tools or languages? Let me reread the data in Python. Again, since I reread the data, define education properly as ordinal. Let's check the bar chart. If I did properly order, yes, I can already see the shape, right? And I can just use the cut codes and get the numerical values of this education as integer. And then I have get dummies function to get these dummies. So I will get dummies for marital status. And let's see, I have marital status merits. First variable TMM is 1 and TMS for single is 0. Derived variables, easy to calculate household number, and I get a derived variable. Right. Now let's do, I don't need, okay, I will just read the data, do some binning. So we have pandas cut function that does equal width binning, so equal range binning. And of course, you see the distribution is very weird. In the first bin, I have nearly half of the population. In the last, only 31 cases. Qcut does equal height binning. It's not getting exact number of the same exact number of cases in each bin because these bins never overlap. So I have all of values 33 in the first bin, and this interval is open on the left side. In Transact Sql, this can overlap. And cut function can also be used for custom binning, and you define borders of the bin as a vector, and it's not over complex, and I get custom binning for age. Now let's do the same thing in R. Reread the data, order the education properly, get the proper graph, and we just use as integer function and add education as integer to my data frame. And this one is using again the levels of the factor. We have package dummies, and in this we have function dummy, which is provided in pandas in Python out of the box. We can use within function to add a derived variable and add marital status as integer. So first it is numeric. Let's use as integer to change it to integer, and then calculate household number of people in the household as integer, similarly like we did in R or Python. We have also cut function in R. Actually, function in Python was copied from R, and we can do equal width binning. Interestingly, that for equal height, we don't have a function out of the box, but I created my own function. So I created a function for equal height binning that will do the same thing as did Untitled function in Transact Sql, equal height binning. And this is the actual formula for the entropy if you want to play and check that with equal height binning we are getting the maximal entropy. You are free to do it. I also provided the code. I will ask the organizers how to upload the code, and there is also calculation for entropy. So you can also use these calculations. Actually, I did it in R. So you can also use this calculation to check that you really get higher entropy with equal height binning than with equal width or custom binning. Anyway, we are at the end of this presentation. I will check the questions, but before that, thank you very much. And of course, let's thanks to sponsor again.